Good afternoon to you all. So today we will discuss about geodata processing using Python. So during the course of lecture, I will be covering the basic introduction to Python, then some basics of geospatial data. Then we will see how do we read and write various types of geospatial data using Python. So here I am assuming that all the all the people viewing this program have some basic understanding of a programming language. So I will not be covering the basics of programming. So I will be just covering the basics of Python programming language. So we'll start with introduction to the Python. So what is Python? So Python is an interpreted interactive object-oriented programming language. So what is programming language? Programming language is the language in which a developer or programmer interacts with the computer. So there are two types of programming languages, either interpreted or compiled languages. So Python is one of the interpreted language. Moreover, Python supports multiple programming paradigms. So in Python, you can write your program either using functional programming approach, or you can say procedural programming approach, or using object-oriented programming. So Python supports both type of programming paradigms, either object-oriented or function-oriented programming language. Next, Python combines remarkable power with very clear syntax. So when you write a program in Python, it looks like you are writing something is in plain English. So the syntax of Python is quite clear. So even if you don't have much exposure to the programming language, just by seeing the program, you can infer the information from the program. So it has quite clear syntax. Next comes about the distribution available, various distributions of Pythons available. So like C, there are multiple distributions of C programming languages available. Like you can say that Turbo C, ANSIC, or other flavors. So similar way, Python also comes in multiple distributions. So I will be using one of the most popular distributions of Python, that is people are using for data science or some other applications, that is Anaconda Python. So I will be demonstrating it using Anaconda Python. So these are the distributions of Python available, like Anaconda Python, Active Python, Win 9x Python, or Portable Pythons, and so on. There are multiple distributions available. Then plus one is standard distribution, that is called Python. So that interpreter is implemented in C programming language. But here I will be demonstrating it using Anaconda Python. So Anaconda Python is most popular Python distribution among the data science community. So people are using extensively the Anaconda Python. Next comes, why do you choose Python? So the most compelling reason for using Python is it's friendly and easy to learn. So you can learn Python as I explained previously, Python's syntax is very clean syntax. So it's like plain English. Plus, it is quite easy to learn. So even if you are new to the programming, you can pick up Python quite fast. So that is one of the most compelling reasons for using the Python. Next, Python is powerful and fast. So Python has a lot of features, a lot of libraries available, so that you can pick up it very fast. Plus, the execution of the program also it takes very less time. It's quite fast. Plus next is it runs everywhere. So runs everywhere means Python is a platform independent programming language. So generally what happens, if you have used C or C++, so if you write a program in Windows, write a program for in C for Windows operating system. So the same program, if you are moving to Mac or Linux tomorrow, so the same program will not run there. So you need to modify your program according to your platform. So but Python's, once you have written a program in Python, so that same program can run on any of the platform. So either you are using Windows, Linux, or Mac, or Unix. So you write a program once and it runs on every platform. so lets you work more quickly and integrate systems easily. So anyway, as I explained, that Python is quite easy to learn, so you can work more quickly. So as according to one of the surveys, a programmer who is writing programs in Python may be 3 times more productive than a programmer using other languages. So anyway, the reason for using Python for our geospatial processing is because there are a lot of open source libraries available for geospatial data processing in Python. So this is also one of the reasons why we use Python. Next is Python's documentation, tutorials, and guides. There are a lot of help available in the forms of tutorials, guides, and community support. So if you are getting into any of the problem, you can get the solution of your problem. You can ask to some forums. There are a lot of tutorials available. So there, plus the beauty about this is constantly evolving. So new changes, people make new changes and they release their software with associated documentation as well. So then, so you have a plenty of resources available at your disposal, so that you can it will help you in tackling any problems. So next, let us start after this about geospatial data. Anyway, in your previous lectures, you must have heard about it. I will just, for the sake of completion, I will be covering geospatial data. So what is geospatial data? So if you read the standard definition, geospatial data is about geospatial data is data about the objects that have a location on Earth's surface. So for example, suppose you are saying that location of a building. So location of a building means when you say in terms of its latitude and longitude. So that particular, so it means that whenever you are attaching the location information with your object's attributes. So like you are saying that this building is situated at this latitude and longitude, or the temperature of this particular place on the earth. So then the data becomes geospatial data. So whenever you are attaching with the objects in location information with the objects attribute information, that becomes a geospatial data. So plus geospatial data in addition to the location information, plus it could have temporal information as well. So like you can say that the temperature of this place over last 10 years, like you can make a time series. So on the day 1 this temperature was this, day 2 this, day 2 this. So when we are associating location, plus it could have a temporal information also attached to it. So that is called geospatial information, geospatial data. So basically, if you divide geospatial data, there are broadly geospatial data is divided into 2 categories. One is called vector data and another is called raster data. So what is vector data? So vector data represents objects on the Earth's surface. So any object on the Earth's surface using their latitude and longitude plus, so any so in vector data we represent the object using their latitude and longitude, or it could be a combinations of latitude and longitudes like lines, polygons, etc. So when you represent so like a point, so you can represent a city using a point or a road using a polyline. So similar way, the boundaries of a country can be represented using a polygon. So what is point data? So point data is a pair of coordinates, latitude and longitude, that represents the location of point on the Earth's surface. So for example, you can say so if you are representing a building as a point in a map, so that is a point data. So all these points have latitude and longitude information. So any point object on the Earth's surface can be represented using point data. So it could be a building, or suppose if you are going at very large scale, so even the city can be represented using a point data. Next comes lines. So point was just represented using its latitude and longitude. So now a series of points represent a line. So here you can see that we have multiple points connected together. So series of points connected together, maybe straight or otherwise, are lines. So what you can represent using line, maybe center of some road, like some road if you want to represent. So road can be represented using line, or rivers can be represented using line. Next is polygon. So polygon it is a series of points or vertices that defines the outer edge of a region. But generally what should happen? Polygon will be a closed body. So wherever your starting and end point will be the same for polygon. So with using polygon you can so the boundaries of any city, country, continents, etc. can be represented using polygon. So in vector data can be represented as either using point, line, or polygon. So depending on your scale or convenience, you can represent different objects using either of these basic constructs. So like here you can see that the map of India it is showing the different the state boundaries using different polygons. So here you can see that this is a this is a typical vector data of showing vector data showing the outline of India's different states. Next is the raster data. So raster data is a 2 or 3 dimensional array of data values such as the pixels in a photograph. So raster data represents objects or variables on the surface as a matrix of values in the form of pixels, cells or grid. So raster data is represented using a matrix of values. So any image if you see very closely or like how it is represented, how it is stored in the computer's memory. So any raster image is stored in computer's memory using 2-dimensional or 3-dimensional matrix of integers or floating point numbers. So the examples are satellite imagery or any aerial photograph. Those are the examples of raster data. So even like here you can see that you can represent spatial variability of temperature, elevation or rainfall, or so here you can see that these are the different points, different grids on the surface of Earth, and these the temperature in each grid is represented using a number. So this number can be so like this you can represent, so instead of surface in temperature of the surface of the Earth you can represent elevation, rainfall at each point on the surface of the Earth. Plus suppose if you are raster image you can have, so this is a single layer. In raster image you can have multiple layers as well. So all the different layers can represent temporal information as well. So like here if you see, this may be the temperature, this will be the temperature in this area at time t0. This may be the temperature at time t1, time t2, or it could be a image in different different electromagnetic bands. So like here you can see this is a typical, this is the combination of vector as well as raster data. So here you can see the outlines of the countries are represented using polygons, and the temperature or rainfall data is shown inside here, inside this. So any continuous data, whenever your data is continuous, so that can be represented using as a raster, or whenever your data has discrete boundaries, so that can be represented using vector data. Now next comes what is geoprocessing. So geoprocessing is manipulating the geospatial data, either raster or vector data, to get some information out of that data. So that is called geoprocessing. So you have a lot of data available to you, and you want to extract some useful information so that that information you can use it for any purpose. So that is called geoprocessing. Now let us see, I will start with raster data processing. For the raster data processing, I will be demonstrating a very quite this is very special library called Geospatial Data Abstraction Library. So GDAL is an extremely popular C++ library for reading and writing geospatial data. Actually, this basically the GDAL library is written in C and C++, but it has bindings available in various other programming languages like Python, .NET, Ruby, or even Java. They have bindings available. So if you are programming in Python, Java, so then you can call the functions of GDAL library from the your host programming language environment as well. So the GDAL is most powerful geospatial data abstraction library. So it supports data processing in vector as well as raster. So plus actually a lot of proprietary softwares are also based on the GDAL library. So this is the basic raster data model of GDAL library. So every image in GDAL raster data model is represented using a data set. So all images or raster data is represented as represented is abstracted using a data set object. So data set object. So it's like whenever you open an raster image using GDAL, so the GDAL returns you an object called data set. So this data set in turn will have multiple bands. So suppose if your image is multi-band image, so this particular so the data set will contain multiple bands. Plus it will have the associated geo transformation information of the image also available. So this geo transformation information helps you in knowing the in converting this pixel number and line number to the real world coordinates. So with the geo transformation and projection information, you can project this particular raster image on any map. Plus every band will have data, as I explained previously, that raster data is represented using matrix or cell of values. So every band in turn will have some data array, plus it can have some associated overviews of that images of that band. So that will be the and at different resolution for drawing it on the image. So suppose if your image is very big, so very large image is there, so and then when you are zooming it out, so then you need at spatial resolution also. So at less spatial resolution, multiple overviews of that image also will be available. So this is basic raster model. So every image is represented using a abstract data set. So data set will have multiple bands plus geo transformation information. Then every band will have a data associated in that band, and it can have some overview. So the overview images. So overview images will be the images which are at coarser resolution, so that the rendering on the screen is faster. Because when your image is very high resolution image and you are looking the entire image together, so if you draw that image at native resolution, it takes a lot of processing time plus memory also it consumes. So for that, whenever you are zooming it out or going to the country level or somewhere, then the overview band will be rendered on the screen. So for today's demonstration, I will be using something called I am using Jupyter Notebook. So Jupyter Notebook, either you can install using Anaconda Python, or directly if you don't want to install anything on your system, you can just directly go to the Google Colab. So if you search on Google Colab, you need just to have an Gmail account, Google account. So if you just search on Google Colab, so Google Colab is a hosted environment. So directly even you can run this code. So here you need not install anything on your local system. So you can just go to the Google Colab and you can start writing your Python code directly here. So basically, if you see in Colab has two types of cells. On the top here, if you see, there is written like code and text. So code will contain your executable Python code. And whenever you are writing, suppose if you want to write some notes or insert some images, so there are two types of cell. One is code cell, another is text cell. Code cell will have your executable Python code, and text cell will have some description, like suppose if you want to write some text, this is sample text. Or because Jupyter Notebook is like Jupyter Notebook is just like your notebook. So you are writing your program in your notebook. So you just write some code plus some images, anything you can insert on this text cell. So suppose if you are going to, then if you want to write code, you can just insert plus code, and if you want to write some text information, you can insert. So depending on your requirement, you can insert different type of cells in the notebook. So I will not be using Google Colab, I will be using Anaconda Jupyter Notebook installed on my local system. So once everything is done, installation and all the things are done. So for first thing you need to import the GDAL package. So in Anaconda, suppose if you have already installed Anaconda and GDAL on your system, so first thing you need to import GDAL library. So for that, import from OSGeo. OSGeo is the name of the package and GDAL is the library available in that. So from OSGeo, import GDAL. So this will import GDAL library to your environment. Then anyway, I am using another package called OS. OS I am just using here for changing the directories and so on. Even actually it is not required right now, but anyway. So first thing you need to import these things. So for running the cell, you just need to click here run. So with run, import library is installed. So now what is happening here? Actually my data I have stored in H drive in an RMS new data folder. So what I am doing first I am changing my working directory to this particular directory. So if you don't do this, then all the time you need to give the absolute path or full path of your data file. So I don't want to give the full path of the file. So what I am doing, I am just changing my working directory to the directory where my data is available. So os.chdir changes my working directory to NNRMS new data. Now in this folder I have a file named L3 NH44 M14 something something October 15.tif. So this is a list 3 image of some area near Haridwar. List 3 image. So now let us see, we will see that how do we open and visualize this particular image using GDAL. So anyway, here I have just defined a variable called file name. So in file name I am just storing the name of my file. So first thing, for reading the file you need to call the GDAL.open function. So as I explained, so GDAL.open will return you an abstract representation of image using a dataset object. So now GDAL.open. So GDAL.open takes actually you need to pass minimum one argument, that is the name of the file. So I want to read this particular file, so I am just passing on the variable file name. So GDAL.open file name. So it returns me a dataset object. Now suppose if I print ds or just give ds, it prints the information about this particular data set. So what it says that this is ds is a type of OSGeo GDAL.dataset. So this is a proxy for SIG object. Actually here we are not using C or C++, so we are using the GDAL's Python binding. So in GDAL's Python binding, this uses something called SWIG. So anyway, you need not think lot about it. So once you open a file, it returns you a data set. So now as I explained in GDAL's raster data model, a data set will have associated bands. So multiple bands will be available and geotransformation. Let's now extract one by one these informations. Now suppose if you have read an raster image. Now suppose if you want to query what is the width and height of your particular image, the image you have read. So now suppose if you want to know what is the height of your image, or what is the width, first thing, what is the width of your image. So if you call on this data set, whatever ds it has returned, GDAL.open ds.rasterXsize. If you call this ds.rasterXsize, it returns you the width of your image. So you can say that width of the image is 1151. So there are 115 pixels in your image in the x direction. Similar way, suppose if you want to extract the height, so here you can go ds.rasterYsize. So ds.rasterYsize returns the height of your image. So it says your image has 11151 pixels in the y direction as well. So this particular image L3 NH44 M14-9750 4th October 15.tif is an image of size 1151 cross 1151. Now as we said that every data set will have the projection information, projection and geotransform attached to that image also. Now suppose if you want to query which coordinate system or which is the projection system, in which projection system the image is stored, so that if you want to query, you need to call on this particular data set ds dot get projection. So ds dot get projection returns you the projection associated with the image. So if I run this step, it prints, this is a coordinate system GeoGCS. So this particular image is stored in GeoGCS coordinate system. So this particular image is or projected using geographic coordinate system. Next, suppose if you want to retrieve the affine transformation information of your image, so that you can extract using ds.getGeoTransform. So ds.getGeoTransform returns you the affine transformation information of your image. So if I actually, the geo transformation is a 6-element tuple. So its first element represents the long longitude of your 0th pixel. Also, and gt. So first element is the longitude. Then second element is the pixel spacing or resolution in the x direction. Then third element. So if I print gt, just let us. So this is the affine transformation of this image. So this first element represents the longitude of origin. So 0, this is the longitude of 0th pixel. Then this is the resolution in x direction. Then this represents the rotation of the image in x direction. So suppose if the north is up in your image, so then this number will be 0. Or if the image is rotated, if north is rotated by some angle, so in x direction, so this number will represent the rotation. So similarly, next, this element is the latitude of origin's pixel, 0th pixel. Then next is the rotation. If north is up, this also number will be 0. Then this is the pixel resolution in the y direction. So here for printing this, I am printing this way only. Origin 0, so this 0th element and this element. These elements are representing the coordinate or latitude and longitude of 0th pixel origins. Then these are representing GT1 and GT5 are representing the resolution in x and y directions. So this represents this. Now suppose if you want to convert any line number or pixel number to its real coordinates. So suppose if you want, so then in GDAL there is a function available called GDAL.applyGeoTransform. So GDAL.applyGeoTransform converts anyway in your image, like if your image is in form of matrix. So every pixel is like the address of every pixel is referred is using line number and pixel number. So suppose if you want to, if you know the line number and pixel number of your pixel, and you want to convert like this particular pixel, like this line number and this pixel number represents which location on the earth, like you want to know its real world latitude and longitude. So for that there is a function available called GDAL.applyGeoTransform. So it takes 3 arguments. First argument, you need to pass it the geotransformation information. Then you want to pass the pixel number and line number. So it says that this particular pixel has this latitude and longitudes. Now suppose if we want to know the we want to calculate the 4 corners or extent of we want to extract or calculate what are the extents of our image. Then you want to calculate. So now we can call the same way GDAL.applyGeoTransform. So upper left corner means 0th pixel. So GDAL.applyGeoTransform at GT and 00, it returns us the latitude and longitude of 0th pixel. Similar way, now upper right corner will be pixels width and y direction still it is 0. Then similar way, lower right corner will be our x, there x will be 0 and y will be equal to the width of our image. So similarly, lower right corner will be represented using our pixels width and height. So this way if you calculate, this gives the 4 corners of our image. Now once this is done, now suppose if you want to know how many bands are available in your image, so that you can call extract using calling ds.raster count. So ds.raster count returns you the number of bands available in your image. So it shows that this is a 4-band image. Now this we have extracted some basic information about image. Now let us see that how do we extract the matrix or pixel values of the pixels and visualize how the image looks like. Now first we will read a single single band raster, then we may go to the multi-band raster. So in this I have a file named L344 band2.tif. This is a single band image. Now let us see that how do we read this particular image. So here I have just defined a variable called file name that contains the name of the file. Next, similar thing like we did in the previous case, jidal.open. So jidal.open and pass it the name of the file which you want to open for reading. So jidal.open file name, it returns a ds. Now similarly, now suppose if you want to know what is the size of this image and how many bands are there, so the same function I am calling but all together, ds.raster x size, raster y size and raster count. So it says the width of image is 1151. So there are 1151 pixels in x direction. Similar way, there are 1151 pixels in y direction, and this particular image has a single band. Now once we got this information, now suppose if you want to extract band 1 values, pixel intensities of image in band 1. So for that there is a function available in our data set, ds.getRasterBand. So ds.getRasterBand fetches the band data from our original image, our image. So ds.getRasterBand, then you need to pass it an argument like from you want to fetch which band. So you need to pass it the argument as the number number 1. Suppose if you want to fetch band 1, actually in the JIDAL bands start from 1, 2, 3, 4 and so on, not it doesn't start from 0. Suppose if you want to fetch band 1 of your image, so then you can just call ds.getRasterBand and pass it an argument band number. So here I am fetching the band 1 from my raster image. So band equal to ds.getRasterBand. Now once I fetched the band, I can extract multiple metadata or array or data values from my or pixel intensities of that particular band. So for that, what you need to call? You need to call, once you have fetched the band, you can just call band.readAsArray. So band.readAsArray returns a numpy array. So it is returning pixel intensities for all the pixels in band 1. So data equal to band 1. So it returns a 2-dimensional array. So if I just print it, it is printing a number. As I explained initially that every raster image is represented using a matrix of numbers internally in the computer's memory. So now here you can see that this particular image internally is represented as a matrix like this. So this is the pixel number 1 or 00, origin pixel has the pixel intensity 75, the next pixel has 71, 73 and so on. So this way you can see the data associated with the image or how the image is actually represented in the computer's memory. So just by seeing this number you cannot get anything. So let us see that how do we visualize these numbers. So how do these numbers make an image? So for visualizing the image, we will be using a library called matplotlib. So matplotlib is one of the most popular library in Python for plotting. So it is used extensively for making charts, graphs, or image plots, etc. So I will be using I am first importing matplotlib.pyplot as plt. So for drawing an image, so first you need to create a figure in matplotlib. So I am first creating a figure of size 25 by 5. So on this particular figure the image will be drawn. So I am just calling plt.figure, figure size 25 by 5. Then once this is done, then you need to, for showing the image, you need to call plt or this matplotlib.pyplot plt.imshow. So if you call plt.imshow and pass it the numpy array, what you read from using GDAL. So then you, if you pass it, it returns you an image. So here you can see that this image looks like this. So anyway, the contrast of this image is not very good. So but these are the pixels. So later in the coming steps, we will see that how do we improve the visualization of this image. The contrast of this is not poor, so it is looking quite dark image and you cannot see anything. So in the subsequent steps, we will see that how do we improve the visualization of the image. Now this is shown in with some default color map. Now suppose if you want to change the color map of this image, you can pass the to plt.iamshow function a different color map. So now suppose if you I want to show it is in hot, or suppose if you want to increase the size of your window, you can just call. So instead of 25, suppose if you want to see 45 by 15. So this way you can change the size of your image on the display. Now suppose if you want to extract what are the maximum and maximum or minimum pixel intensities in your image. So you can just call data.max or data.min function. It returns you the, so in this particular image the maximum pixel intensity is 338 and minimum intensity is 42. And now suppose if you want to plot the histogram of your image, so you can call just plt.hist and pass it the numpy array. Then it shows you the histogram of your image. So plt.hist and pass it the numpy array or matrix values which was returned to you using which was returned to you by GDAL. So it takes a bit of time. So you can see this is the histogram of our image. So it says that maximum of the pixels are lying in the range 50 to somewhere around you can say 100. So though the maximum pixel intensity maximum is 338 and minimum pixel intensity is 42. But actually if you see the histogram of your image, you can see that most of the pixels, or even you can say that more than 95% of the pixels intensities are in the range 50 to 100. So you must have studied about different image enhancement techniques. So one of them is like you can see that histogram equalization or min-max scaling. So there are multiple ways to enhance the visualization or improve the contrast of your image. So here what we will do, here we will use something called clipping. So what we will do here, we will use clipping. So all the pixels which are less than 50 or greater than 100. So that all the pixels will clip in the range 50 to 100. So either you can say that we are ignoring the pixels which have intensity above 100 or below 50, or we are just clipping to them. So any pixel which has the values above 100 will be scaled to 100, and pixel which has value less than 50 will be scaled to 50. So if you want to do this, so what you need to do, you need plt.imshow. So to plt.imshow, you need to pass another argument with the value clim. Clim is clip limit. Clip limit is in 50 to 100. So we want to clip this particular image pixel intensity is in range 50 to 100. And now we want to use the color map, gray color map. Now if I run it, now you can see that the image is same image, but now anyway we have done some basic contrast enhancement and the image looks quite pretty. So this way you can improve the visualization of your image. So once this is done, now you can close. Now this was all about reading a raster image. Now let us see how do we write a single raster band image. Now suppose you have collected data, geospatial data in some form, like suppose you have temperature, you have collected temperature at different latitude and longitudes in your city or in your country, and now you have collected the data and you have stored it in some CSV, some other form, like at this latitude longitude this was the temperature, at this latitude longitude this is the temperature, this is. So this way you have collected the geospatial data about your city. Now suppose if you want to visualize it, because if you see the temperature in CSV file, you will not be able to make out much information out of it. So when you represent this type of information using a raster image, so it gives you more insight of your data. So let us see now how do we create a raster image using GDAL. So now here for this demonstration, I have here a CSV file that is containing global tech map. So here if you see, I'll show you. So here you can see that I have a CSV image with me. So here it says this at, like you can say, at 00s or any latitude and longitude. At this particular latitude and longitude, the value of total electron count is 35. And the next latitude and longitude, like I have moved to the next latitude longitude. So suppose you can say that, so you assume that this was my 00th. So 0 degree latitude and 0, comma 0. This was this at 00. Now next this may be 0, comma 1. So 00 degree latitude, this lat and long, at this long, this was the value. At this lat and long, this was the value. Similar 02, 03, 04. So these are the total electron count at different latitude longitudes. Now let us see that how do we convert it using a map. So this CSV file is covering the latitude range from 87.5 degree to minus 87.5 degree and longitude minus 180 to 180. And in latitude the difference is minus 2.5 degrees. So from one column to second column, the difference is minus. So 00th column is which corresponds to 87.5 degree latitude and minus 180 degree longitude, and next column 87.5 minus 2.5 degree latitude and minus 180 plus 5 degree longitude. Plus this CSV image has 71 rows and 73 columns. So for this, first we will read this CSV file. So I am just importing NumPy library and my data is available on this techmap.txt file. So then after this I will be, so if I see here OP raster 2, if you see in this my particular folder, there is no OP raster 2.tif image. So I will convert this techmap.txt file to raster image or using TIFF file. So I am just giving the destination file name as output raster 2. So for creating the raster image, first you need to create a driver. Driver for which format you want to create the driver for the format in which you want to write your raster image. Suppose if I want to convert it to GeoTIFF or IMG format, so accordingly we need to pass this GTIFF or HFA or ENV file or whatever type of file if you want to convert. So first you need to create a driver for that particular format. Now suppose here I want to create a GeoTIFF file. So what I am doing, first you need to call GDAL.get driver by name. So GDAL.get driver by name. I am just first creating a I am creating a driver for GeoTIFF format. So driver equal to GDAL. So it returns a driver for handling GeoTIFF format. So now once the driver is you got a driver. So next on the driver you need to call a function called create. So driver.create. So you need to pass it an argument like destination file name, in which file you want to store your data. Like once you converted your file, where do you want to write or save your data, into which file. So GDAL driver.create, first argument it is destination file name. Then next is X size. So what is the width of your image? Then Y size is what is the height of your image. Then next is how many bands are in your image. Then next is E type, like in which type of data you want to store your pixel intensity, maybe like 8-bit integer, 8-bit unsigned integer, or 8-bit signed integer, 16-bit integer, or floating point number, or a complex number. So once you first thing you create a driver, then on the driver you call a function called driver.create, pass it an argument like destination file, in which file you want to store your data, width or height of your image, how many bands are in your image, and what is the data type of the pixel intensity. So once this is done, this creates a destination data set. Now for this, first we need to read our techmap.txt. So for reading this, you can use any other function as well. So I am just here using numpy. Numpy has a function called np.loadText. So np.loadText returns a CSV file. So loadText takes these arguments. First, I am passing is the source text file from which I want to read the data, and delimiter. What is the delimiter between two values? So I am using a comma as a separator. Then next is data type. What is the data type you want to interpret it? So by default, what happens if you read a CSV file? Everything will be represented as a string. So now suppose these are numbers. So I want to interpret these string values as 16-bit integer. So if I do this, it returns me a data. Now if you see data, so this has returned a two-dimensional matrix. So this is quite similar to what we have shown when we read a GeoTIFF image. Finally it returned a matrix of values like this only. Now once we have read it, now what you can do, like in while reading we did destination dataset dot get raster band. Now we will, because this is we want to write a single band image, so we are calling get raster band and passing it the band number in which we want to store the data. So destination dataset that dot get raster band is returns the fetches the band 1. Now once this is done, while reading the data we were doing band dot read as array. So now here what we are doing, we are writing to a file. So here we will call band dot write array. So band dot write array will write this particular data. So band dot write array. So if it has returned 0, means it has successfully returned the data to destination image. Once this is done, then you need to call on the destination dataset the flush cache. So if you don't call this flush cache, sometime flush cache method, so sometimes what happens, the data doesn't get returned to the disk immediately. So actually operating system optimizes it, and according to according to its optimization, it might decide to write the data to the disk at later stage. So if you open the image at that particular instant of time, so you will see just a black image. So you will say that there is some bug in the program, but that is not the thing. Actually what has happened, operating system has not written the buffer to the disk itself. So if with flush cache, you are forcing the operating system to write it to the disk. So once this is done, then you can just delete the destination dataset. So memory associated with this dataset gets freed. So this is done. Now if you see here, now the output raster to a GeoTIFF file got created here. Now suppose if you want to read this particular image and visualize that how this my tech map looks like. So what you can do here, what I will do, I will just change the name of this file to op raster 2 and read it. So I have just changed the name of file and remain things are same. So here you can see that if I read this file, raster 73 by 71 I have explained, and it has a single band. Now if I read data, and it reads, now let us visualize this in a bigger plot. So here you can see that we have converted converted a CSV file to a geo raster or raster image for better visualization. You can see the nice map created. Now suppose if you want to attach a color bar to image, like which this color represents which value. So suppose if you want to, then you can just call plt.colorbar. So this color bar will attach a color bar to the image. So here you can see that okay, this color represents this value, this color represents this value. So this way, what we have done, we have converted a CSV file to a raster image for better visualization. So this was all about reading and writing a raster image using JDAL. So now let us see that how do we read and write. This was raster data, vector data. So for reading and writing vector data, we will use another library called GeoPandas. So GeoPandas is also one of the most popular libraries for even actually JDAL OGR can be used for reading and writing vector data, but actually it is a bit difficult to read and write vector data using OGR. So actually GeoPandas is much easier, much easier for reading and writing vector data. So first we will start with the basics of GeoPandas. Actually, the primary data structure in GeoPandas is implemented. There are basically two classes. One is called a Geo Data Frame and one is Geo Series. Actually, Geo or vector data is represented using, you can say that it's represented using a tabular form. So what in this every column, so every column in your table is called a Geo Series, and your entire table is called, you can analogy if you take. So suppose your vector ultimately finally your vector data is represented in tabular form. So you must have seen that with vector data you will have an attribute table attached to it. So what will happen? Every attribute will be represented using a column, right? So in GeoPandas, this every column is called a Geo series. So similar way, there is a special column in your GeoPandas frame that is called geometry. So that contains the geometry of your objects. Then other columns that contain attribute information are like another attributes. So these all each of these columns are called geo series, and your entire table is called geodata frame. So let us see now. Anyway, import. So first thing you need to install GeoPandas and you import. Now what I am doing, I am just importing GeoPandas as GPD and anyway pandas and NumPy. So in this I have a vector data vector or shape file of shape file containing the tehsil boundaries, different tehsil boundaries of Uttarakhand. So I have here right here file name tehsil.shp. Now let us visualize this particular image using GeoPandas in Jupyter Notebook. So I have just defined a variable called vector file with name tehsil.shp. Now like in JDAL you read JDAL.open. So in GeoPandas there is a function called read file. So geopandas.read file and pass it the name of the file from which you want to fetch the data. So I am calling a variable called Uttarakhand equal to gpd.read file. This the name of this particular file. So now if I just print Uttarakhand.head, so it returns me a. So you must have seen if you have handled shape files. So these are the attributes. Like in my shape file, there is an attribute called tehsil. So that attribute contains the name of this particular tehsil, and there is another attribute called district. That is the in which district this particular tehsil is falling. Then there is a special column called geometry. So that contains the geometry of my different objects. This may be point, line, or polygon. So like this is the tabular form. As I explained, this tehsil, this every column is represented as a geo series, and this entire table is called a geodata frame. Now suppose like in raster dataset, there may be a CRS or projection information attached to this particular image. So that if you want to extract from GeoPandas, you can just call your geodataframe.crs method. So it returns you the which projection system this particular file is in. So that gives you the projection information of that image. So it is also in EPSG 4326 or geographic coordinate system. Now suppose if you want to visualize it, so it's quite simple. Your geodata frame dot plot. Geodata frame dot plot plots the all the polygons of your geodata frame. So this way quite easily you can visualize your, then you can customize your visualization according to your need. There are multiple arguments you can pass to the plot function and customize the customize visualization of your vector data. Now suppose similar way, now suppose if we want to subset our data frame. So suppose from this, if you want to extract the boundaries of only tehsils of district Almora. So instead of, you don't want the entire Uttarakhand state, you want to filter out your geometries. So here we have a column called district. So district contains the district of this particular tehsil. Now suppose if you want to extract the which all the tehsils are available are in Almora, that is just if you want to extract. So what we can call subset equal to our original Uttarakhand dataset Uttarakhand, where district is equal to Almora. So this will fetch only the rows where the name of district is equal to Almora. This will filter the rows. So here you can see that it just fetch the Almora. Similar way you can call like where Dehradun. So these are the tehsil in Dehradun district. So now suppose if you want to plot, you can plot. So this way you can clip or extract from a bigger geometry a subset of your geometry using some attribute or any other, you can filter and or anything you can apply there. So now suppose if you want to in this map, suppose if you want to attach the name of tehsil also with your map. So for that you can call annotate function of the matplotlib. So with annotate function you can just attach the names of your tehsil with your maps as well. So with matplotlib annotate function you can attach. Now I am just resetting it. Now suppose that you suppose in your data anyway, in this particular data we don't have population information attached to our. So what we will do here, we will just attach some random population to every district or tehsil in Uttarakhand. Then we will make a choropleth map of population, so that easily you can visualize, okay, this tehsil has this much population, this tehsil has this much population. Suppose if you want to make a map like this, a population map of tehsil. So what we are doing, I am just assigning some random population to every tehsil in Almora. So now if I see, now if you see here, so what we are doing here, we are creating a population a series first that contains 8 rows. Then we are attaching to the Almora. In Almora we are adding a new column called population. So previously if you see, there was no population column. So by adding this line Almora population equal to this population, some random population we generated, so it had attached a new column. So you can see that Almora, Tehsil Almora this much population, Bhanoli has this much population, and so on. So here we have attached the new fictitious population column to our original data. Now let us make a choropleth map for population. So here if you just call almoda.plot, so it just plots the geometries. Now if you pass an argument like we want to color the polygons according to the some particular column, so then you need to pass an argument column equal to. Now if you see that all the polygons are colored in different color are filled with different colors. So these different colors represent different populations. So with this you can make a choropleth map based on some attribute of your vector data. Now anyway there is no legend attached to it, so we don't know what this color, which number does it represent, which number this color represent. So suppose like color bar, you want to attach a color bar to this image. So what you can pass, similar thing, same thing you can do, almoda.plot your geodata frame dot plot, and based on which column you want to color your map, and legend, if you pass legend equal to true, it will attach a legend to your image as well. Here now you can see the legend got attached. So this yellow color represents maximum population, and this dark blue represents minimum population. Similar way you can just change the orientation of your color bar and so on. There are multiple options available. So this was the vertical color bar. Similar way, like suppose if you legend keywords, if you pass label population by tehsil and orientation, you can pass. Similarly, figure size, by figure size, you can change the size of your map. So this way you can visualize a choropleth map using GeoPandas. Next thing is like suppose if you have data available in tabular form, so now and you have some discrete data, not continuous data, and you want to convert it to a shape file. You assume that you have latitude, longitude, and the temperature of some point data. So like suppose if you say I have here the file stations.csv. So you can say that we have some multiple air quality monitoring stations installed across various locations in Uttarakhand. So like these are the latitude and longitudes where this particular station, air quality monitoring station, is located. And like these are the we have the latitude and longitudes of all the our air quality monitoring stations available across Uttarakhand. Now suppose if you want to visualize them in the map, so this, because this is a discrete data, so representing it using vector is the better choice compared to the raster here anyway. So these are point data. So what we will do, we will convert these to a shape file, so that you can visualize either Python using Python or any standard GIS software. So now let us convert this stations .csv file to a shape file. So here I have name of the file. So I am just reading like GeoPandas. Instead of GeoPandas, I am reading it using pandas. So df.head. If I read, so you can see that like this is the station ID, this is the station's name, or this is the code for the station. Then at where it is located, like this latitude and longitude. Similar way for all stations. Now, as I explained, a geodata frame will have a, so these already are the attributes or columns. Now plus a geodata frame will have a special column called geometry column. So geometry column will contain the geometry of our objects. So now anyway here these are the point data. So we want to represent each station as a point. Not, we don't have polygons because we don't have the entire area. Like suppose your station is spread over some area. Now what you are here, we want to represent our station using a point object. So for that first we need to create a geoseries. So gpd.geoseries. So if you call in GeoPandas there is a function available called gpd.points_from_xy. So if you, there is a function in GeoPandas that is called gpd.points_from_xy. So this points from xy convert, if you pass it two arguments like latitude and longitude, so from this latitude and longitude it will convert it to a point geometry. So here we are calling that function gpd dot points from xy, and we are passing it this particular latitude and longitude columns. So what it will do, it will convert all these latitude and longitudes to all so this latitude and longitude will be represented using point 1, this latitude longitude will be represented in point 2, point 3, point 4. So what it is doing, this is converting these entire all both the columns, like all arrows from this series to different points. So either you can call it with a single point like df from point x and y. So this is to convert a single point. Here what we are doing, here we are converting the entire column. So this will be like if you take part of this only, these there will be only 4 points. But anyway, if I see the length of my df, so there are totally 152 rows available in my table. So this gpd dot points from xy, it will convert it to 152 point geometries. Now if you see the geom column, so you can say that every row got converted to a point geometry. So point geometry with longitude and latitude. Once our geometry column is made, then we can just call geopandas dot geodata frame. Geopandas dot geodata frame, and pass it two arguments. First is our basic attribute table and a geometry column. If you have done this, this returns a geodata frame. Like if you see ahead here, so you can see that a geometry column got added here. Now suppose if you want to visualize it, gdf dot plot. So here you can see that inside out all these point, every station got represented as a point. So then later on you can map you can add a base map to this Uttarakhand's map you can put on the background, so that on Uttarakhand you can visualize. So this way you can visualize. Now suppose anyway now until now we have not attached any georeferencing or coordinate system to this projection information on this geodata frame. So for that we can call a function called dataframe.crs. So dataframe.crs, and pass it the argument like our coordinate or projection information. We can pass it as an argument like plus init equal to EPSG 4326 or any other coordinate system. Here we want because we have latitude and longitudes. So this is in geographic coordinate system, or EPSG 4326 is the code for this. So I am just changing attaching the CRS this to this file. So gdf.crs. Now finally, once this GDF is done, now suppose if you want to write it as a save file. Now here you can see that there are already some files. I will first delete these files. And if I just write gdf.to_ file, and I will call it airstations.shp. airstations.shp. So then this will write this file as a save file. So here you can see that this created a file called airstations. Anyway, you must be knowing that a shape file will have multiple associated file also attached with this. So here airstation.shapefile and its associated files, it got created. Now suppose if you want to read it, so either these files you can visualize using any standard GIS software, or directly here itself you can read it here. So like I will call here GDF to GPD dot file, and I pass it the name airstations.shp. So if I plot it, So it plots like this. And then suppose if you want to fetch the CRS information, you can call just gdf.crs. It returns you the CRS information. And suppose if you wish to see the attributes attached to this, you can just put gdf. So it gives the attitude, various attributes of this shape file. So this is all for today's lecture. So what we covered, basically we covered basics of uh, geospatial data. Then we covered two libraries for processing the geospatial data. One is called GDAL, or Geo Data Abstraction Library, for processing raster data. Then we covered GeoPandas library for visualizing and reading and writing some vector data. That's all for today. Thank you very much.